Today we will start chapter 10. So chapter 10, so far till chapter 9, you see we just talk about the regular languages. Today we will see non-regular languages. A language that, what is the definition of regular language? We are now expert of that. We know that any language that can be defined by regular expression, or it can be defined by uh, FA, or it can be defined by NFA, or it can be defined by TG, or it can be defined by GTG. So all these are regular languages. And we know that if it is a regular language, there must be at least one regular expression, FA, TG, GTG, NFA must be one. There may be more than one, but one must be there for from each of these category. And these are interconvertible. It is not possible that it's a regular language and it is missing any one of this. Now, this is the exactly reverse of this. So when we talk about the non-regular languages, a language that cannot be defined by a regular expression is called a non-regular language. So if you have a non-regular language, it is not possible to write a regular expression of that. To define this language by writing a regular expression, it is not possible. If you have a non-regular language, you cannot draw, or there must be no FA possible for that, no TG for that, no NFA for that, no GTG for that. You cannot define these languages which are non-regular languages by any those mathematical um models. Now let's see this example here. So we have this language L, and now for that we need some other mathematical models we will see today. But first, our job is to figure out how we know that this is a regular language or this is a non-regular language, because they are looks very close to each other. So how we find how we create a distinguish between differences between these two languages? What are the ways to find the difference? So first thing is the definition. The language which cannot be defined by regular expression is called a non-regular language. Now we have this language here. If you see in this example, it has first word is lambda, and then AB, then AABB, and then three A's and three B's and four A's and four B's. So by looking all these words, we can say that this language can accept lambda, and it is composed of only two letters, A and B, and A will always be in the leading position and B will always be in the following position. And you will always see a word start from A, end with B. You will never have A there, you will never have only B there. You will never have any word which start from B and end with A. It always has A as a leading position, B as a following position. And it is infinite language. You see dot dot dot, and this is a pattern. We don't care how many A's, how many B's, but whatever the number of A's, how many number of B's, they are same. If you have two A's, you must have two B's. If you have three A's, you must have three B's, four A's, four B's. So anyone, what should be the regular expression of this language? Anyone can try to find the regular expression of this language, like for this thing. You think that, are we able? I mean, it is very important that you answer, because it doesn't matter your answer is right or wrong, but at least we can figure out. Yes, please.
I don't think there is a proper regular expression because the closest would be like A star B star, but then it would have to include like AAB, which it doesn't.
Yes, you are right. And beside A star, B star will have A also, only A, because you can get lambda from B, you will get only A, and you will get lambda from A, you will get only B from there. But here it says only A and B. We have something like that. Let's say if I say A to B2, so it says that two A's and two B's. So for that, but this is different. No, this also does not work. So no, so anyone else, if you come, if you think that we are able to write a regular expression of this, you see, this is very easy language, but it is very hard to find the proper regular expression of that. So now there is one way to represent that, which is algebraic way. And if you see here, we are saying, and look at this second thing. If you have a n and b n, and n can be anything, n can be 1 to 0 to anything onward. So you have same number of A's and same number of B's. So if you see here, we have here n. So this n means whatever the exponential value of A, it will be same for B. It cannot be different. If it is different, then its symbolic representation will not be n, it will be nm, because two different placeholders. Okay, so we do not have nm here, we have nn here. So it means that both should be same. Whatever the value of n for A, the same value we will use for n for B. So this roots, this works, but this is not regular expression. So we can write this in form of this. So now we can say that whatever the regular expression, whatever this language is subset of this language, A star, B star, because A star, B star is everything. It has all A's, all B's, only A's, only B's, and then it follow the order. A always come first, B always goes after that, and it has same number of A's, same number of B's, as many as you like, but it has some other characters also, which is not in our language. So we can say that our language, we can extract that from this big language, but this big language is not exactly like our language. It is not equal to that. It is a superset of our language. So A star, B, so our language is subset of A star, B star. Are we good? So this is good. Now we are saying that if this is the case, let's go to the next page. Now let's try to find FA or any mathematical model to represent that. So we pick one example from A and Bn. We said, okay, if we have A and Bn, what about A9, B9? So we have this language A9, B9, and we want to draw some states and try to find that. So we have these 10 states. Out of 10 states, 9 states have label A, and then you have here label B, and then you want to find A9, B9. So you see that 1, 2, 3, 4, 5, 6, 7, 8, 8, 9, and then then B start 1, 2, 3, 4, 5, 6, 7, 8, 9. So here we did our 9, and we have this A9, B9. So somehow we managed to, you can say that, draw this machine which can work for A9, B9. But very quickly, once we done that, we figure out we have a loop here. If you see that, so there is a loop here in this machine here, and there is a loop here in this part. Okay, so now if you have a loop, so nobody can restrict you that you can take one ride on this loop, or you can take only two rides on this loop. So you are allowed to take as many rides as you want on the loop. So now this create a discrepancy here. Now let's see here. So if we want, we can have more rides on this part, and that makes increase the number of A's. Instead of 9, it will make it 3. So once you have 9, here you have 9, 10, 11, 12, 13. You take one more round and you have 13, and then you have 9 here. So this means that it is possible by this machine to accept this word also, A13, B9, whereas this is the violation of our language. Our language says Bn. So Bn, sorry. So whatever the number of A's, it should be the same number of B's. So it is violation of that. So this is something which, so it shows that this machine is not good. It's not perfect. It does not. It can accept by creating this machine. You can validate some words which are valid words, but it also validate some invalid words. So this is not good machine. So because we know that in previous chapters, whenever we draw TG, FA, and FA, it never accept any invalid word. It always reject that or fail that or crash that. It never pass that those words or accept those words. So this machine is not good. So now you see one two examples that if you have a, so this is our non-regular language. So this shows that A N B N, this is our non-regular language, because you have a language, you try to write a regular expression of that, we try our best. It is very simple language, but we are failed to figure out what will be the regular expression of that. And then we try to draw the FA, close to FA, NFA, whatever you want to say that this machine. Uh, we didn't figure out that how this machine will work. So this shows that this is a non-regular language. Okay. Any question here? So now once we figure out that this is very hard to find the this is not, it is not possible to find the regular expression or FA or any mathematical model, existing mathematical model of for non-regular languages. We find a mechanism now. We are saying there is a one way. It is called pumping lemma. Once you apply pumping lemma process on your any word, and this after applying this process on your word, if your word does not violate the definition of the language, it means this word belongs to a regular language. But if you apply a pumping lemma on a word and it violates the definition of a language, it means that it is not a regular language, it is a non-regular language. Now I give you one scenario. Let's say we have a word, we have a language which starts, which have uh, which accepts lambda. We have a language which accepts lambda, and it starts with B, or it can start with A, and it has always even number of A's to accept the language, and it can have any number of B's in between. So now here is a loop here. You see here. So now if I want to, if I say that this language, so or let's say make it more easy for you. So it will always be odd number of A's. So now if you, so this is a language now, yes? So what should be the regular expression of this language? This language gives you guarantee that you have you have always either one A or three A's or something like that. What should be the regular expression of this language? We saw this, but okay. I mean, this we discussed this in previous class, I believe, somewhere in somewhere in this last slide. So now, if you see this, uh, I have my question is if I have a word which is uh, B A B. Is this a valid word for this language or not?
Yes.
Very good. Now I want to take more rides on this machine. Okay, so I want to take more rides on this loop here. You see, there is a loop here. This is a loop. This is a loop here. I want to take more rides on that. So now I take more ride and I said, okay, B. I start from B. It is not necessary you always have B, but let's say I start from here. And then I said 1A, second A, and third A, and then B. This is a valid word. Yes? Now, so this is a valid word, because if you see one, two, three, this is a valid word. And now if I decide, if I want to beef up this word again, how I beef up? I can have more rides on this loop. So I said, okay, let's find another word. One, two, three, and then another two, and then B. So as much as I can beef up this word, I can take more rides on a loop, on any loop. I have more loop here. I have more rides here, let's say. So it does not violate the definition of the language. So this is a regular language, because when you have a regular language and you have a word and you take more rides on the loop in your regular language, and you will beef up the size of the word, it will not violate the definition of the language. Still, this is a valid word. Still, this word, if you pass this word, it will be accepted by this machine. Look at the sizes of these words. So do you understand this concept? Anyone has any issue with this? So this is a very nice concept, that what we just proved. You have a regular language, you have a loop there. Somewhere in your language you have one loop. We try to find, we might have more than one loop there is in our language. We here, you see, so we have one loop here, second loop with AA, and this is our third loop. Just pick one loop and beef up the word. And if you beef up the word, it should not violate the definition of the language. So we pick this loop, which is AA, and we increase the size of the word, and we see that every time, regardless how many times we take right on a loop, our word, the resulting word, is a valid word. It does not violate the definition of the language. It is never possible that you create a word, it is violating the definition of the language, but machine says, oh yes, this is a valid word. No, it is not the case. You can have wrong word, but machine will reject that. So all the valid words, it will be accepted by this machine. So this is one concept. So now if we apply the same mechanism on non-regular language, and we beef up the size of the word, it will violate the definition of the language. Now let's see here. So anyone has, first of all, anyone has here any confusion on this concept? So then
So
yes, please.
what is X, Y, and Z in this example? Is there an X, Y, and Z in this example?
No, that I did not explain that yet.
Oh,
So
okay.
I will explain that when we talk about the pumping lemma. And so I am just here making a point, and then now I will take this point to the non-regular language, and there I will explain you what is X, Y, and Z. So before that, do you understand what I just explained?
Yeah, I think so.
Okay, very good. So I mean, guys, you need to answer the question when I and tell me that yes or no if I ask you, please. So this is the only way here I can understand that you are listening and you understand what I'm saying, because this is very important concept. And my experience says student always make mistake in this. Okay. So Quinton, are you happy with this?
Yeah, I'm happy enough for now.
That's great. Okay, so if you are happy, so let's now let's take this concept to the pumping lemma. So now when we say in our, so now we have a language, because here we know this is a regular language. Let's say we have a language and we have no idea this language is regular language or this language is non-regular language. Okay, we are blind, we have no idea about that language, let's say. Now we apply this mechanism which is called pumping lemma on that language and this will tell us, oh, this is regular, oh, this is non-regular, how it is. Let L be any regular language. Okay? So let's say we have a regular language and this language is, let's say, your L language. So we are saying that, let's say we have a regular language which is L, and this is infinite, it can have infinite words, it's an infinite language. then there exists, so we have a one word of our language. Let's say we have a word, like in this previous example, you have one word B A B, and so you are saying I want to divide this word into three parts. I want to divide this word into three parts. One is X, one is Y, one is Z. And I guess that there might be more than one loop in my language, but I guess that I just need to find one loop, and which is, I guess this is at this position Y. There is a loop here. So now I'm saying that my loop is at this position, which is Y, and it's raised to power n. So always you divide your word into three parts. One is X, one is Y, one is Z, and Y part you consider that it is on the loop. So here I consider that this part is X, this is Y, this is Z, and this is on the loop. So now if this is a regular language and n is equal to this, you can have any number of n. If this is a regular language, and then if you increase your word, the size of the word, it should be a regular language. This is what we are saying here. So if you have a loop there, so now if you have, so now if you see one example here, then you can better understand this thing. So now if you have one word which is complete word, you into three parts. One is X, one is Y, one is Z. And what you are trying to do, you are, by looking the word, you are trying to find that which part is on the loop. So this is what you are trying to do. So now you are saying, okay, I think that this part is on the loop. It is just a guess. And then if it is on a loop, and I can take more rides on a loop, it should be the same thing. So then I said, okay, might be this is on the loop, and because I consider this is on a loop, so instead of taking one ride, I take more than one ride, second ride also. And I, instead of XYZ, now I have XYYZ. I take second ride also on that. Now, if XYZ belong to a language, XYYZ should also be belong to the same language. If it is not the case, then it means that we need to find another instance. After 3 4 times different instances, we try that, and if all instances does not work, all guesses does not work, it means that this is not a regular language. It is non-regular language, because non-regular language has this property that if you beef up the word, it should violate the definition of the language. And XYZ means, now I came to the your question. XYZ is three parts of your word, and you can see, you can bust using the human wisdom and try to find that which part has a loop here. Let's say I have a word something like this, B A B. So I clearly see here that A is coming. Let's say my word has and definition does not work. So BAAB. So now it has always two A's there. So now I can divide my word into this part. One is X, one is Y, one is Z. So now if BAAB is a valid word, and this is X, this is Y, this is Z, then X, Y, Y, Z, because you cannot increase the size of X, you cannot increase the can increase the size of the word. So now you increase that X, Y, Y, Z. So what does it mean? B will be as it is, one Y for A, second Y for A, and Z is for B. And now check that. Is this a valid word according to your language? If it is a valid word, it means this is good. If this is not a valid word, it has two meanings. First meaning, it is not a regular language, it is a non-regular language. Second meaning might be you are guessing wrong. It is not on the loop. This is not the valid Y. So then what you need to do? Then you need to do some changes here. So another guess. So B. So consider second scenario. Might be this is my Y and this is my Z, and there is no X, because in this X and Z may be lambda. Both can be lambda, maybe one can be lambda, or both can be lambda, but y will never be lambda. So y must have some word. So it is highly possibility that your whole word is y, or you have y or z, or you have x or y, but it is not possible that you have x and z but no y, because y, x and z, x and z can be lambda. Both can be lambda, but y will never be lambda. Y will always be present there, where y is not the empty word, such that all words of. Okay? So x and y, x and z may be empty word, but y will never be empty word. Okay, so this is the basically idea behind that. So now this is something which is called pumping lemma for state that is. So now if you see, if xyz belongs to your language, if you pump that, so xyz, xyyyz, so this is also on the language, and that's the reason that because you pump y, so you are saying that y raised to power nz, because you only thing which can beef up the word is y. So you, and y, whatever the y, we assume that this is on a loop. Okay, let's see one more example, and then might be it will also help you to understand that. So look at this machine. So first of all, is this FA or not? Labels are good. Start state, final states are there. Every state has, first state has B and A, second has A and B, third has A and B, four has A and B, 5 has A and B, and 6 has A and B. So it is taking care of garbage collection. This is a valid FA. It has letter by letter. It has one start state. Final state we do not care, but it do have two final states. And this is perfect FA. When it is perfect FA, we can say that this is also an FA and it is also TG, because implicitly all FAs and all NFAs are TG. So now we have one word which is this word, and we want to see that whether this is a valid word of this machine or not. Okay, so now let's see if this is a valid word or not. So B, 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 we start from here, one B, second B, third B, A, B, sorry. Okay, so B, 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 and then A, and then B, and then A, then B, and then A. So we stop at the, we finish at the final state. So this is a valid word. It should be accepted by this machine. Okay. So did you figure out that there are loop here? So if you see the machine, we have in this word, we find two loops there. One is here, loop, and second is here. See, so we have two loops here. So now sometimes you do not have machine in front of you, you have just word. Like when I ask you question, I will not give you machine, I will just give you word. So it is just a guess. By looking at the machine, you can guess that where is a loop there. So now we try to find the loop here, and what we say that okay, might be we have loop. So we need to divide this machine into three parts. So we try to find loop here, and where you have a loop, consider that part y, and other parts are x and z. So now you are saying that okay, I have this whole word here. My first b is x, and then bba is y, and then remaining part is my z. If my this guess is right and I beef up this word, then the resulting word should also be valid by this machine. So now I have this word b and BBA, and then B, when I write why it is B A B A B A B A. Okay, so this is, so I said this is my X, this is my Y, this is my Z. So if this is a good, if this is a valid case and Y is proper on the loop, so now I want to beef up my word. What does it mean? X, Y, Y, Z. So now what is B, 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 A, B, B, A, and B, A, B. A. Okay, so I have this thing. So now I need to see that if this resulting thing is valid or not. B, 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 A, B, B, A, B, A, B, A. So you see, I beef up my word and the resulting word is also a valid word. It means my guess is right. I successfully find the right part of my word which is on the loop. And when I beef up my word, this is also does not violating the definition of the language. It is still valid. It is accepted by this machine. It means this machine language is a regular language and this word belongs to the regular language. I apply pumping lemma on that. Make sense?
What was the goal in selecting X, Y, and Z? What are you trying to do?
So we are trying to find so what we're trying to find. So we have a word and we just do not it belongs to some language. In this case, it is very easy. You have FA in front of that, and you before applying this, you know that this is a regular language. But let's say you do not have FA in front of you, and you do not know that this language is regular language or non-regular language, and you want to figure out whether this is a regular language or this is a non-regular language. And now you want to divide this word into three parts and you want to figure out the which is y part here, and y part we guess that this is on the loop, and when you beef up the word, so you will have more than one y because y raised to power n can be 1 2 3 anything. So if you have two y's, three y's, four y's, you can take more rides on a loop. The resultant word should belong to that language. It should not violate the definition of the language. Okay, so this is basically what we try to do. We want to beef up the word, increase the size of the word, and if by increasing, if it still maintain and validate the language, it means this is a regular language. If it, but this is not the property of non-regular language. If it is a non-regular language, if you beef up the word, it should violate the definition of the language. Does it
Got it.
answer?
Thank you. Yep, that's perfect.
Okay, so now you will now this is we just see this with respect of regular. Now we apply this on non-regular language, and there you can get better understanding. Look at this one. So we have this language. This is A and BN, and we know that this is not a regular language. Okay, let's say. So now we have one word, and this word is this word. Okay, so what is this? 3 4 5 6 7. So basically it is this 3 1 2 3 4 1 2 3. So it's a big word, long word we have. This is one word. It has same number of A's, it has same number of B's, and we want to see that whether this word, for sure, this word belong to some language, yes. So now we want to see that whatever this language is, this a regular language or non-regular language. So our job is to find, divide this word, apply pumping lemma on that, and see what's going on. So now my first guess is I think that exactly this way, divide this into x, this into y, this into z, and when I pump it, so I put how I pump it. I will add more y here. So I am saying now x y z, and now what is x y y y z? What does it mean? 1 2 3 4 b, and then 1 2 3 4 b b b b, and then last three b's. So do you think that if you see this one now, if you combine all this as one word, do you think that this, no, as it is here, then
Professor,
b,
you're cutting out a bit.
oh, my voice is not coming, is it good now?
It's intermittent. Yeah, I hear that.
You want me to restart the audio?
It seems to be working now. Can you just repeat what you said?
So I'm saying that if I have this word, which is here, I show here one word. I divide this word into three parts: X, Y, and Z. This whole thing is one word. I divide this into three parts. So if you combine X, Y, Z, this will make one word. And now I assume that Y is on the loop. And if I pump this word, how you pump, because y raised to power n, so you want to add one more y or two more y's or as many more y's there. I just add one more y, and I by adding one more y, look at this one, this is x, this is y, this is y, this is z. Now do you think that this is according to the definition of the language? It has same number of a's and same number of b's, but look what happened. It says A will always be in the leading, whereas here in the leading, B in the following, then A in the in between, then B there, and then B there. So A comes in between B and B. So this is not the case. So A will never come after B here. But in this word, when you pump that, so it comes in between. So it has two meaning. First meaning, this is not a regular language. Meaning might be our first guess of considering y is wrong. Might be this is not on the loop because we have no any formal method to figure out which part of the word is on the loop. We do not have machine in front of us, so we are just guessing. Might be our guess is wrong. Okay, so what are the other possibilities? This is my first guess. If middle section y is going to be made entirely of a's, then after pump a to x, y, y, z, the word will have more. So now my first guess is, let's say, I'm saying, I have, I consider whole this thing, let's say, you know, x and z may be lambda. Let's now what happened if you pump this language, will say y, y, z. So if you do that, you will have more number of and less of b's. Yes. So this is not the according and once you do that, this will violate the definition of the language. Language says a and b n, same number of a's, same number of b's. So my first guess is wrong. Might be I choose. So now when my first guess is wrong, so it's keep cutting out. Maybe restarting the audio software may help.
Yeah, it's getting really bad right now.
Okay, okay. Let's try to fix it. So avoid video and audio connection. Disconnect audio. So am I good now? Do you guys hear me now?
Yeah, I hear you now.
Is it good?
Yeah, it's good right now.
So Gunnar, are you? Is it good? Okay. I don't know who was. Riley, is it good? Okay. Okay, that's great. So I hope that you didn't miss. You understand what I am saying. So I just pick one guess, which is y and z. First part as y and second part as z, because we know that might be x or z is lambda, or any one is lambda, or both are missing, both are lambda. Y must be there. So I need to figure out which part is on the loop. I think my first part is on the loop. And if I consider my first part as y, I beef it up, and now I have y, y, z. And I check that it is not according to the definition of the language. The language is a and bn, both number of a's and b's are same, whereas yyz means more number of a's and less number of b's. Now my my
It's still having problems with the microphone.
see what's going on. Now I'm very close to the my modem. So now I speak slow. I try to speak slow, so might be that is a case. Uh, so let me know if it is still cutting. Okay. Uh, so now I take a second guess. What is my second guess? If the middle part is y is composed of only b's, then the word x, y, y, z will have more b's. So let's say I'm saying my second guess is that this is x and this is y. And now if I pump, it is x, y, y. If I do that, it has more number of b's. It is again violation of the language. Language is a n b n. So my second guess is also wrong. Okay. So might be the third guess is that y part must have some positive number of a's and some positive number of b's. So might be I have this is x, this is y, this is z. And now if I pump, I already show you this example. It has same number of A's, same number of B's, but it has a problem that you will have A after B there, because once you pump Y, you will have A, B, something like that here. You will have again A after B, which is not the case here. Language says it is an bn. It should not violate the definition of the language. So now after considering these three guesses, there is no other possibility that you can choose that might be this is my y, because you consider all possible possibilities of considering y. You consider only a's, you consider only b's, you consider combination of a and b, and I think that we exhaust all our options. And now, after considering these three cases, there is no other case which left, and we can say, oh, might be my guess is wrong. Let's say this y. No, we don't have any option left. We apply all possible possibilities of considering y. And after applying all possible possibilities, we are not able to figure out which part is on a loop, and it is not violating the definition of the language. It means when we apply pumping lemma process on this language A and B N, we never get a valid word. Yes, so it means this is a non-regular language. Whereas in previous example, you saw that when we apply pumping lemma on a word here, it never violate the definition of the language. It will also be a valid word. In this case, we try three cases. It does not work. And now we have no option left. We have no scenario left. And that we can say that this might be a y, because these are the only three possibilities. Only A, only B, or combination of A and B. This is your word. And after applying that, you figure out that okay, I apply pumping lemma on my word. Um, and after applying pumping lemma, my language is not satisfying. It is not validating any scenario, and this proves that this is a non-regular language. You guys understand now what's going on, and my voice is good or not?
Yeah, it's good.
It's good. Okay. So, but do you understand this process of pumping lemma? How you use that to figure out regular and non-regular language? I mean, this scenario is clear. This example is clear to you. Very good. So if this is good, so now another question which you should ask: how many scenarios we should consider? How many times we consider that this might be y, this might be y, or here in this example I consider three different scenarios. So I do not want you to consider one scenario. I want you to consider at least 3 to 4 different scenarios. Like we have three scenario here. Okay. So sometime, somewhere you feel that I exhaust all possible options. So and you will notice that it will not take long. So might be after applying 4 scenarios or 3 scenario, you will figure out that I exhaust all my options. Now I do not have any option left to find another piece of y in my word, and that's it. So there you stop. Okay, so somewhere from 3 to 4 different scenarios from same word. Now let's see another example. We have this theorem here: equal all words with the same number of a's and b's. So equal is equal to so this is, so all words with the same number of a's and b's. So so now it says that you have lambda here, and a b b a and a b b. So it does not care that what is the order of a, what is the order of b, but it says that it should have same number of A's and same number of B's. Whenever you count, if it has 2 A's, it should have 2 B's. If it has 3 A's, it should have 3 B's. But place order does not matter. It can start with A, it can start with B, it can end with A, it can end with B. A or B can come anywhere in the word. So now equal is a not regular language. So now we know that equal is not regular. So we know that equal is non-regular language. Okay, let's say this thing. Now we are taking intersection of equal with another language, which is A star B star. Okay, so now if equal were a regular language, now we know that A star B star is a regular language. Now if equal is a regular language, then this is, we know that. Let's say we do not know this. Let's say we do not have this information. This is, we know this is a regular language. We learned this already. We have no idea about this language. We don't know what is this language, regular or non-regular. This is, we know this is regular language. This is, we have no idea what is this. Okay. So now A and Bn would be the intersection of two languages. We figure out that A and Bn is intersection of these two languages. So now A and Bn, we figure out by the previous page that this is also non-regular language. So now once we know that the resultant thing is non-regular, and we are taking intersection of two languages, and one of them is regular language, and what is this language? Without any doubt, we can say that this is non-regular language, because we learn everywhere in previous chapters, if you have two regular languages, their union is regular, their concatenation is regular, their clean star is regular, their intersection is regular. We learn this and we prove this. We draw the FAs of that. Whereas when we apply here intersection on two languages, out of one we know it is a regular language, other language we don't know what is this language, and whatever the resultant thing we get, we prove that A and Bn is a non-regular language. It means this language must be a non-regular language, because if it is a regular language, it is never be possible the resultant thing will be non-regular. We prove that here. We prove it here. Look at this one. We have proofs of that. Okay, so that's the thing, that we know that this will be a non-regular language. Equal is a non-regular language just by this method, this lemma, that two regular languages, their intersection should be regular. It should not change the behavior of the language. Whereas in this case, when we have two languages, their intersection is not a regular language, it is non-regular. And we know that the two languages, two participating languages, out of that, one is regular and other is not, other is we don't know. So for sure other is non-regular. That's the reason that the resultant language is not regular language. This is something we prove here. Now we will see that this is another language. Okay, look at this one. This is A N B A N. So this is, we have this language. It says that you always have one word B. How, if you write the word of this language, it means that n can be 0, n can be 1, n can be 1, 2, 3, 4. If n can be 0, so A will be lambda. So you will have only B there, or you have A, B, A, B, A. B will always be there. Same number of A's will be in the, if they are there, in the following and the leading position of of B. So this language, and we need to figure out that this is a regular language or this is a non-regular language. Okay, so now we have this. What is the way to do that? We pick any one word from here, and we do the constructive proof of that. And then we apply pumping lemma on that word, and then see that the resulting word is violating the definition of the language or not. So let's see. So we are saying we pick, let's say, this word. Okay, so A, B, I pick this word. Observation 1. If the Y string contains the B, this is Y, this is X, this is Z. Well, how you pump that? So when you pump, so it will be X, Y, Y, Z. So it means A, B, B, A. This is violation of the language. You never have two B's there. So observation 1, if Y string contains the B, X, Y, Y, Z would contain two B's. So this is not good. So we think that either one of the answer is right, whether this is a non-regular language or might be our initial guess to consider Y is wrong. Okay, so let's try to figure out second scenario of Y. If the Y string is all A's, something like this, either in the start or in the end. And now if you pump that, what should be your language? Sorry, we do not have X here. So A, and B, A. Yes. So this is again violation of the language. You have same number of A's and same number of B's. So we try this one, or might be this is with the other part. Let's say this way. This is Y. This is X. This is Y. Now if you pump that, it will be A, B, A. This is again violation of the language according to observation 2, because you have same number of A's, you should have same number of and on the both side, whereas it has two A's in the falling position and one A in the leading position. It is violation of the language. And once you have this word ABA, so I don't think we have any scenario left. We consider B only, and then we take A with that, and then we take another A in the falling position with that, and I think we exhaust all the options for consideration of Y, and we conclude that this language ANBAN is a non-regular language. So we just prove that by this conclusion. Are we good? So always consider, pick a word from a given language and only consider one word, and use multiple scenarios of Y on the same word. Exhaust all possible options of considering Y. Might consider XYZ, consider XY, consider YZ, or different position of the Y, including X and Z, all possible options. Don't go, I'm not expecting you should go for more than 4 cases, just 3 to 4 cases. That's it. And then conclude that this is regular or this is not regular language. Okay, and here we finish this. So any question, guys? So please, you are free to ask a question. Don't ask, so I will go to the next chapter.
I do have one question.
Yes, please.
Do X, Y, and Z have to be in that order?
What do you mean?
So, does it always have to be X, Y, and Z, or can it be like Y, X, and Z?
No. It should be X, Y, and Z. It can be X and Y only. It can be Y and Z only, but it will never change the order, like Z will come first and then X and then Y.
Okay.
Are we checking if X, Y, Y, Z is in the language, or are we checking that all of? Okay, first of all, it is not star, it is n. Y raised to power n, Z is in the language. Star has different meaning, n is different meaning. Uh, we, technically, we should check all possible options of y, like more than two. You can check more than two y's, but here we do not check more than two y's. We just check two y's. And but we try to combine left and right of x and z with different scenarios of y. Sometimes we add different x, sometimes we miss x, sometimes we add z, sometimes we consider z is not present there, z is lambda. So, it depends on the word. It will give you idea that which option left here. So now if you have this word a, b, a, what are the options you will choose? You will think this is x, this is y, a is x. So if you have this word a, b, a, so this word tells you that you have one option is this, second option is this, third option is this, and that's it. Or might be this is, or the another option, this whole thing is y. Let's say aba is y. So, and once you've done that, you will no option left to make any permutation or combination of aba, and then you exhaust all the options. So don't need to check more than two y's. If it is good for two y, it should be good for three y's also. So is this answer your question, Quinton?
Yep.
Okay, thank you. Any other question, guys? Questions? Good. So if we are happy with this, I already posted this here. And if you see that chapter 10, and you have quiz today, and June 4 you have exam, I'm sure you can see that. I have chapter 11 also, I posted, and let's see what is in this chapter. Oh, let me delete all these things. So now we have this chapter here, which is, so do you want me to go to the next chapter, or you think that we are good and we should finish this, only we should stick with this chapter? Guys, quick answer. You want me to continue or stop here? Okay, silence means yes.
I think we
Go
should
ahead.
stop just because we have the quiz today, and also we have a test coming up.
Oh, so you want me to stop here? Austin, this means that you want to stop here?
Yes.
Okay. Okay. So, I mean, no, I don't want to be rush because the coming chapters are not that hard. And I know that some chapters are very small and we can finish actually two chapters in one might be in one lecture. So I'm not in hurry. So we can do this, finish this chapter in next class. We are not, we are okay. So let's stop the recording here.